Hi folks, this is your next lesson on the straight line. This is on gradients and angles, and we'll be looking at page 3 of your departmental notes, so page 3. That's just a continuation of what we've done last week. So as a wee bit of an introduction, what I've got here is a straight line, and what I'm concerned about here is the gradient of this straight line. Now we know from before that to get the gradient of a line, we just take the vertical change divided by the horizontal change between any two coordinates on the line. So in this case, to work out the gradient of this line, we just do the vertical change over the horizontal. Now, as you can see, I've marked in a wee angle here, an angle theta. What I want to do is just take this wee right angle triangle I've made under the straight line and have a wee closer look at it. So there's that wee triangle. Here's my angle theta down here. Now, using our knowledge of SOHCAHTOA, you'll remember that in a right angle triangle, which I'll put the right angle in as well, in a right angle triangle, this would be my opposite side, opposite the angle that I'm concerned about, and this is my adjacent side and my hypotenuse. So SOHCAHTOA tells us that if I was to do the opposite divided by the adjacent, similarly where I did vertical divided by horizontal, opposite of our adjacent is what we call the tan ratio. So tan of that angle is equal to O over A. Now remember that O and A in this case were your vertical and horizontal. And we know if we do vertical over horizontal, well, that's just the gradient, that's just M. So what we get is a nice new formula for the gradient. So the gradient of a line can also be given by this formula here, M equals tan theta. Now, one very important point to make here is that the angle that we use, if I draw a quick line here, not a very good one, but that's my y-axis and my x-axis. If I draw a straight line here, the angle that we use is always in the positive direction of the x-axis. Now notice this blue line here makes two angles with the x-axis. So it makes one on the left hand side of it, so like that, and it also makes one on the right hand side. When we use the formula M equals tan theta, we always use the angle to the right hand side of the line. And the x-axis, you see the wee arrow there pointing in the positive direction of the x-axis. So that's what it means. So always use the angle to the right of the line. Now, just a wee recap on our tan graph. I've drawn a wee rudimentary tan graph here just so you can recap on it. Got a few different lines, a few different diagrams of different types of gradients, and we'll just compare them to our tan graph. So first of all, is if we have an acute angle, so this is where our line is sloping up the way, and the angle to the right hand side of the line is between 0 and 90 degrees. You'll notice that a line like this has a positive gradient. And if we just quickly look at the tan graph, for an angle between 0 and 90 degrees, the tan graph is always positive. Therefore, a positive gradient for any angle between 0 and 90. Then we get into the case where we actually have a 90 degree angle that the line makes with the x-axis. So 90 here, 90 here. In this case, if we have a vertical line, we have a line that has an undefined gradient. So the gradient cannot be calculated in this case. And if we just quick look at our tan graph again, at 90 degrees the tan graph is actually undefined as well. So a wee connection here between the tan graph and the gradients of these lines, and it follows this formula. Continuing on, now if we have an obtuse angle, so an angle bigger than 90 degrees but less than 180, you'll see that this time, from an obtuse angle in there, our line is now sloping down the way, which means that we have a negative gradient. And again, a wee quick look at the tan graph tells us that between 90 and 180 degrees, the tan graph is negative now, it's below the x-axis. So our gradients are all going to be negative for any angle between 90 and 180. And then our final case is where our line makes an angle of 0 degrees or 180 degrees. And in this case, we just have a horizontal line which has a gradient of 0. And again, I'll just check my tan graph. At 0 degrees, the tan graph is at 0, and at 180 degrees the tan graph is again at 0. So the gradient is 0. So just showing a wee connection between the gradients of our lines and what we know about the tan graph. Now, if you make sure you're on page 3 of your notes, we'll just go and try some of the types of examples we'll be asked. For now, all these examples will be calculator, so you can use your calculator for each of these. However, when we go into trigonometry, there'll be certain angles which you will be expected to be able to calculate without a calculator. But we'll just use our calculators for now. So, example 1. So we're told straight away a straight line makes an angle of 50 degrees with the positive direction of the x-axis, and we're asked what the gradient of the line is. Now, first of all, the wording of this question is actually really helpful. So if it states the positive direction of the x-axis, immediately what that means is we're going to use m equals tan theta. So if it uses that phrase, immediately m equals tan theta if we want to work out the gradient. So I know it's going to be m equals tan theta already. Just bear in mind that if you were to work out the gradient of a line, usually we would take 2 coordinates and we'd use our y2 minus y1 formula. We can't use it in this case because we don't know any coordinates. So we needed a new formula for the gradient. So once I've identified that it is m equals tan theta, the next thing I want to do is I want to just double check that I've got the correct angle. So this is where the positive direction of the x-axis comes into play. First of all, my line makes 2 angles with the x-axis, one to the left and then another to the right. Now the positive direction of the x-axis is to the right of this line, so I'm looking at the 50 degrees in here. So I can input my angle now, so m equals tan of 50. And like I said, we can just use our calculator in this case. So on your scientific calculator, just tan of 50, and you'll see we end up with 1.19. And so on. There's no specificity about rounding in this case, so 1.19 would be totally fine. Okay, so example 2, just a wee bit different. So again, we're asked what is the gradient of the line shown in the diagram. Now, again, if it's asking for a gradient, you should be thinking in your head, do I use y2 minus y1 formula, y2 minus y1 over x2 minus x1, or do I use any other formula? So in this case, we don't have any coordinates, so we cannot use y2 minus y1 over x2 minus x1. So what we're going to have to do is find a different formula. We're given an angle, so therefore it suggests that I'm probably going to use m equals tan theta. Once I've identified that I'm going to use this formula, the next thing I need to double check is that the angle that I'm using is the correct one. So again, the line is going to make 2 angles, one to the left and one to the right. We always want to use the one to the right of the line, i.e. the positive direction of the x-axis. So what we're going to have to do is work out the missing angle here. And these two are supplementary angles, so we just do 180 subtract 62 degrees, which leaves us with 118 degrees. So the angle we should be using in this case is 118 and not the 62 degrees. And just bear in mind, I don't think I've explicitly stated it, but the angle is always the angle above the x-axis, not this wee angle below it. It's always one above it. Okay, so m equals tan theta. Therefore, m equals tan of 118 degrees. And it's worthwhile looking at your graph right now and just double checking, do I expect the gradient of the line to be positive, negative, 0 or undefined? In this case, my line is sloping down from left to right, so I would expect this to have a negative gradient. And your calculator should do this for you anyway. So if I type in tan 118, it comes out perfectly as negative 1.88. There we go. So I'm fairly happy with that. That's definitely a negative gradient. Now, the other type of question we may be asked is, what if we're given the gradient and we want to work out what angle it makes with the x-axis? So we sometimes may have to use this formula backwards as well. So example 3, we're told in this case that we have our line, the line makes us a degrees with the positive direction of the x-axis, and we're told the gradient of the line, but we want to work out what angle must it be. So if we're ever asked about what angle a line makes, that's going to be an m equals tan theta, because that connects the gradient with the angle. So straight to m equals tan theta. Now in this case we know what m is, so m is a half. So a half equals tan, and the angle we want is a degrees, so tan a degrees. And then to solve this, if we remember back to our trigonometry from last year, we do the inverse tan of a half. And then just fire that in your calculator. And we should end up with 26.565, blah, blah, blah. So I'll go for 26.6, just to make it nice and nicely rounded. 26.6 degrees. And I'll just double check that the diagram looks roughly right. I'm happy with 26 degrees for A. Seems reasonable. Okay. And then example 4. So find the angle that the line joining these 2 points makes with the positive direction of the x-axis. So again, a wee bit different again. This time we don't even have a diagram. Now, we're told this statement again with the positive direction of the x-axis. So this is suggesting that I'm going to need to use m equals tan theta. And it's actually wanting me to find the angle as well. So it's an m equals tan theta question, but backwards, like example 3 was. Now when we do m equals tan theta backwards, in order to work out the angle, we need to know what the gradient is. But unfortunately in this question we don't know what the gradient is straight away. So the first step would be to realise that, oh wait a minute, I need to know what the gradient is before I work out what the angle is. So what we'll do is we'll take our 2 coordinates that we know, and we'll use the other gradient formula on it. So I'll call that x1, y1, x2, y2. I'll just do this in a different colour as well. So I'll go and try our y2 minus y1 formula first to get the gradient. Now if you had 2 coordinates, you would always use this formula to get the gradient anyway. So y2 minus y1, 7 take away 3, all over 4 take away 2. So we end up with 4 over 2, which gives us 2. So a gradient of 2. So what we can now do is we can take that 2 and plug it into that m equals tan theta to work out the angle. So 2 is equal to tan of theta. Therefore theta is the inverse tan of 2. And again, just in your calculator you can work this out, and that gives you 63.43 degrees. I'll call that 63.4 degrees. Nicely rounded. Okay, so using m equals tan theta and to work out a gradient and also to work out an angle. Just bear in mind again the wording of the question. Positive direction of the x-axis immediately tells you you're going to use m equals tan theta. The other clue that you're going to use it is if you don't have 2 coordinates but you still need to work out the gradient. So there's a chance that you'll be using m equals tan theta, and there are other formulas that we'll end up using as well in that case, but that's one of your options. So you can now try the gradients and angles worksheet, which I've put on Teams. Answers are with it as well, and just again feel free to just ask if you have any questions on it. And for anyone that's wanting any more information, just one other thing I wanted to point out was, if I have a line that goes through the x-axis like that angle there, just note that, see, once I get from 0 all the way up to 90 degrees, and then beyond 90 degrees get our obtuse angles, all the way to 180 degrees. Once I start going beyond 180 degrees, I just start repeating the original lines again. So we only really need to consider angles between 0 and 180 because it's just above the x-axis. So just if you've wondered why I've not used any angles beyond 180 degrees, that's why.